Hi everyone, Clelia here from LlamaIndex, and today I'm going to walk you through building a LlamaAgent from the ground up. So first of all, what is a LlamaAgent? A LlamaAgent is basically our brand new product, which is currently in private alpha, that lets you build and deploy workflows, both as a backend and as a full stack service on our cloud platform, Llama Cloud. More of this later when we will actually see a LlamaAgent in action. So first of all, let's understand what we want to build here. So we want to build an anomaly detection workflow and anomaly detection LlamaAgent for pest control. And the scenario is very simple. You have to imagine you are a farmer and you have a crop, and your worst enemies are agricultural pests, which are normally insects that eat your crop, lowering the productivity of your farm. So in order to understand whether or not a pest can be of damage, can be detrimental for your productivity, you have to monitor, and you generally divide your crop into smaller sub areas, and you sample the population for these sub areas, counting the individuals. If you have a low number of individuals per area, this means it's good, but if you have a high number of individuals per area, this is very bad, and it can lead to a lower productivity because the pest is eating the crop. So how can you avoid all of this? How can you keep the pest under control? Obviously, the monitoring is only the first step, because then once you produce the data, you have to compare this data with historical normal population data. So normal population data, and you can do this via a vector search engine, for example, Quadrant, which is the vector search engine that we're going to use today, which stores basically the data as vectors. And you can imagine that basically what we can do here is the same. We can represent the count and population samples as matrices and as vectors, and we can compare them with the vector data stored in our vector search engine. And so what happens here is that we can now then calculate the distance of the recorded data and the I would say reference normal population data, and if the distance is too high, that's probably an abnormal population growth, an anomaly that has been detected. And what we do then is basically start pest management, or put into place a certain number of techniques to reduce the pest population. So how are we going to build this workflow? So in order to build this workflow, we will do basically we will have basically, I would say, three main steps. The first step is that we're going to receive from our front end, and we will see this in a second. We're going to receive the data as a string, as a CSV string, and so we're going to turn that CSV string into a polars data frame. Once we have that CSV string in a polars data frame, we can do two things. We can visualize the data, so as a heat map, a density plot that displays how the population is distributed across the different sub areas of our crop, and we upload this image to Supabase, or in general any S3 compatible storage, so that we have this image available to pull back into our front end when the workflow is done. And then always like again from the polars data frame, we can represent the polars data frame as a vector, and we can use that for to search for similar data points in Quadrant. So obviously, if there are no similar data points because the distance of our data generated data is too high, we will probably run into an anomaly. So an anomaly will be detected, and so we will say, okay, this data is anomalous. Whereas on the other side, if there are similar points, this means that our data is probably non-anomalous. So this is how we will perform anomaly detection. And once we will have this workflow deployed, you will see that we will have a front end which will allow us to generate data and to send this data through the whole pipeline of our workflow, which at that point will be a LlamaAgent, a deployed LlamaAgent that will generate all the data and pull them back to the front end with the heat map image, and with the anomaly detection prediction. So that is basically what we're going to build today. We're not going to dive deep into how we implement the front end, but we're going to see how you can build the LlamaIndex agent with code. So here we are, and we're going to start building our LlamaAgent with code. So first thing that we need to do is we need to set up our directory, our repository, and I am going to use UV as my go-to tool for Python projects. So I would say UV init dot, and I will initialize basically my repository. I will delete the main.py file because we do not need it for now, and I will create a directory called src anomaly detection. So sorry, src. I will then add some like default files, and this is basically what we need to start. So we need a Python package, or basically a Python script that we can reference from our pyproject.ml file. And so what we're going to do is basically we're going to add some details, as for example the build backend, which is not that much of an interest to us, and we're going to add actually the reference to our workflow, to what we will build as a workflow for our deployment. So basically we will say that the workflow will be placed under anomaly detection workflow.main workflow, which will be the name that we will give to our workflow instance, and we will set basically the name of our deployment with Llama deploy. The name of the deployment is anomaly detection workflow. It will inherit the environment variables from our .env file, and it will be deployed on Llama Cloud, setting Llama Cloud equal true. So let's now build our workflow, and let's get back to our sketch to see what we need. So first of all, we need polars, then obviously we need Supabase, we need quadrant, and we need obviously Llama index workflows. So we're going to add all these dependencies, and we're going to install all of these dependencies. As you can see, V is extremely fast, and it also created for us a .vnv, so a virtual environment, which we can proceed by activating. Okay, in this virtual environment, we have all our dependencies installed. So this is great, this works. So now what we need to do is we need to build, first of all, our third-party, I would say, dependencies that can help us upload to Supabase, search for quadrant, and obviously also represent our data as a polars data frame. So let's start with the first step, which is representing our data as a polars data frame, and let's create something that's called data processing. Let's put in init.py file, and let's create also a processing.py file. Here we will define our data processing logic. Then obviously we need some S3 storage logic, and so we will create an S3 storage, and we will then create also here an init.py file and a storage.py file, and then obviously we need the quadrant utils, the vector search, or I would say even better, vector store. We'll create also our init.py file, and we will create a vector store.py file. So we will populate all of these files one by one. Let's start with our processing file, and in our processing file we will define a data processor class that first of all validates the data, ensuring that they are in the format that we expect them to be. Then it loads the data into a polars data frame, and then it plots the data into a heat map that is saved into a temporary file, and that will be used to upload obviously to Supabase. And speaking of Supabase, we define here an S3 storage class under the S3 storage utility, I would say, package and module. And obviously we need to connect to the S3. We need to connect to Supabase first of all. So we define a bunch of like connection parameters. Then we basically create a store function that is able first of all to upload the image to a storage space on Supabase, what they call a storage bucket, and then obviously we will create a URL for that. We will get a URL for that image, and we will return that URL if nothing bad happened during the storing operation. So basically all of this is just to have a URL of the image to display that into the front end. Last but not least, our anomaly detection client, our anomaly detection class, anomaly detector, which has to connect to a quadrant cloud instance. So we have some also here connection details, and we have to basically get a quadrant client, and then we define anomaly by just creating a vector from our data frame, our polars data frame, and then querying the points and having basically a score threshold that is the minimum distance, that is the maximum allowed distance between the points and like basically the query vector for these points to be considered similar. And so obviously this is an anomaly if the length of the points in the result is 0, but if we do retrieve similar results, obviously this will be not anomalous data, this will be normal data. So now that we have all our utility third-party modules ready, we can create our workflow. And we will create it here, as we said, under the workflow module. We will have an init.py also here, and we will create obviously 3 files. A main.py, which will contain our main workflow, and as I like to separate the concerns here, I will have an events.py file that will have all the events in my workflow, and our resources.py file that contains all the resources that my workflow is using. So let's fill them up. First of all, let's fill up the events file. And so we will obviously define an input event with the data as a string, as we said, because we expect the front end to send the data as a CSV string. The first obviously step is processing data, so we will expect that obviously we will have a produced heat map as an image, and so we will return the path to the image. We said it's a temporary file that we just use for storage, for like temporary storage of the image on the local machine, and then obviously we have the image stored on Supabase, so there's no need, we will remove that image. Then we will proceed by uploading the image, and so we will return the URL of the image, and last but not least, we will provide the output of the workflow with obviously whether the data are anomalous or not, the URL of the image, and whether there was an error during the execution of the workflow, because there can be an error wherever between the starting step and the last step. So we have to handle also that. So now let's move on to resource. As resources, obviously what we need is basically the S3 storage. So we have our S3 storage, we have the Supabase URL, the Supabase API key, and the Supabase bucket ID, which we'll put into a .env file, and which will be available also to our LlamaAgent when we deploy it. We will see it in a second. And we have the anomaly detector. So these are the resources that we can inject within our workflow, and then obviously we can define the workflow state. So we have basically an internal representation of the workflow with variables such as the data frame, which are available throughout the whole workflow execution. So now that we're ready with both events and resources, let's define our workflow. So the workflow is this one, and as we said, we define it in the main file, and the workflow is this anomaly detection workflow that first step has the data loading, the data process loading and processing. The second step is uploading the image, and the third step is detecting the anomaly. As you can see, our workflow uses the workflow state as an internal representation, as well as our resources like the S3 storage, annotated here, and the anomaly detection resource, annotated here. So we basically have everything in place. Our workflow will run through the first step with the input data coming from the input event. Then if everything goes well, it will produce a data processed event, which will go to the second step. If everything goes well and the image has been uploaded, it will produce an image uploaded event with the URL of the image. And finally, it will search basically for the anomaly, for an anomaly, and so it will produce an output event with the anomaly evaluation and with the URL of the image. If anything goes wrong in the previous step, those steps will produce a output event reporting an error occurred while processing the data or while uploading the image. Last but not least, as we specified in our pyproject.toml, the name of the variable that has the workflow is workflow. So we have to specify a variable in the main submodule called workflow and assign it to anomaly detection workflow with a timeout of approximately 5 minutes. So this is our workflow, and this is basically ready to go. So we can from here try to, let's say, preview our workflow deployment, our workflow backend deployment using LlamaCTL, which we can install in our environment. You pip install LlamaCTL. So now that we have LlamaCTL, we can take a look at the different subcommands that we can use, and we can, in order to preview our workflow, we can do LlamaCTL serve. This will kick off basically a build of the environment. We already have all the packages installed, so this will start basically our backend application here with everything that we need. Obviously, this won't work because we haven't yet defined our environment variables, but you can see that you can preview the deployment, you can preview all the endpoints, and for example, we can take a look at presumably like the health of our application just by running a simple curl command. and just like curl the health of the server, and you can see that the status of our server is healthy. So yeah, you can see obviously all the things that have been logged here. So once we have everything set up, we only need basically the environment variable. So what we're going to do is we'll create a .env file in which we will basically put all our environment variables. So here they are. We have all the environments variable in our .env file that is specified here as this environment source of our Llama deploy, or actually LlamaCTL in this case, tool. And so we can now do LlamaCTL serve, and this will actually obviously work also as a backend service. So we could post basically to this run endpoint, and we will get a result of the workflow. But we won't do that right here. This is just for you to see that you can also preview your deployments in your environment. And what we will now do is that we will create a deployment. We will create a workflow deployment directly on GitHub. So we will create a GitHub repository, and we will create a deployment. So first of all, in order to create a GitHub repository and create a deployment, we will need, obviously, we will already have the directory is already a Git repository because UV init also creates a Git repository. So we just need to add all our changes and commit them. Once we have that, we can then create a repository on GitHub using gh-repo-create, but you can also do it through the browser user interface. We can create these, and we can just describe it as an anomaly detection workflow. So we'll set the visibility to public. We'll add a remote. We'll call this remote origin, and we will push all the local changes to the remote. So now we have our repository created, and so we can deploy our LlamaAgent directly from this GitHub reference. So first thing that we can do basically to deploy the LlamaAgent is to LlamaCTL deployment create. What this will do is will prompt us to create a deployment, but there will be a problem here. If you are not authorized to create a deployment because you are not authenticated, like you're not logged into Llama Cloud, you want to first run LlamaCTL auth, and like LlamaCTL auth, and you will see basically you can do a LlamaCTL auth login, or you can use a API token to log in to Llama Cloud. So I am already logged in, so we're not going to do that again, but you will have to do that. You will be prompted to do it if you are not yet logged in when you create a deployment. So let's now create a deployment. As you can see, we say anomaly detection workflow has the name of our deployment. We have our GitHub repository, and the GitHub reference is our branch. We don't have any config file. We don't need personal access token because we are already actually authenticated, and we can see that LlamaCTL has already pulled in all the secrets from our environment. So now what we just need to do is we just need to save this and basically create the deployment. And as you can see, it already gives us the endpoint on which the deployment is going to be created. And as you can see, the deployment is now pending, but the environment is basically getting started. UV is installing all the dependencies, and now we can start seeing the informations from the application, and you can see that the application has actually started, and presumably in a second our status will go from pending to running. So we deployed our application. So basically what happens here is we deployed our application, but maybe we want to change something. Let's say I want to be more specific here, and I want to say I am sorry, but an error occurred while processing data, and I can copy this message, and I maybe want to push this to my repository. So I will have get add, get commit -m, and I will push. So now, obviously, what you would expect is your deployment to be up to date with this. So in order to put your deployment up to date, you just run LlamaCTL deployments update. And you will be prompted to select the anomaly, like the deployment you want to update. We will select anomaly detection workflow, and as you can see, we updated from the first commit to the last commit. As you can see, you have the last commit here. So you updated your deployment, and you want to see that the deployment is being rolled out. So you run llama-ctl deployments get, and as you can see, our deployment is right now rolling out its update, and it won't be available for a while it's rolling out, presumably a couple of minutes or even less if your bootstrap time is lower. And as you can see now, this was even less than a couple of minutes. The status is now running. But how can I access this from the internet, from a HTTPS endpoint? So in order to see this, you just need to go to cloud.llamaindex.ai, so to your personal account, and you need to go to agents if you have access to the agents. And as you can see here, we have our anomaly detection workflow, and you can take a look and take a pic to whatever here is needed to run the workflow, and you can basically use this and also test out this endpoint directly, this endpoints directly from here. So now that we built everything, now that we did everything, let's look at this in action. This workflow that we just deployed, let's look at it in action. And so in order to look at it in action, I created this demo hooking up this workflow here, the anomaly detection workflow, with a very, very simple front end that we saw here, which is a Go web server deployed with deploy, which has a generate data command in which you can generate synthetic data. In this case, we generated anomalous data, and then you can go and detect anomalies just by pasting the generated data. You can now run evaluate data, and this evaluate data will, in this case, detect an anomaly and return you the generated heat map, exactly as we expect our workflow to do. We pull the generated heat map from Supabase and we detect anomalies using Quadrant. So this is pretty much everything, from building basically a LlamaAgent from scratch. If you are interested and if you want to register to LlamaAgents, you can input a couple of data, and obviously we will get back to you regarding your possibility to access. But basically, as you can see, our LlamaAgents are what we would say a secure and self-contained environment, a cloud environment accessible to you through your Llama Cloud API key that helps you basically deploy workflows that you can use as backend for projects like this one that I just showed you. I hope you enjoyed this video, and I hope to see you in the next one.